lectures we have talked about economics of drainage project, and now I mean the irrigation economics we are going to cover in this lecture. So basically the irrigation economics. So economics is the fundamental decision criteria of irrigation and drainage engineering. So engineering economics analysis uses basically the project life. We have explained the project life into three basic types. One is actual life, economic life, and financial life. So that's project life and expected rate of returns, and to compute the expected present and future costs and benefits of proposed irrigation and drainage system. So in this what happens, so knowing the project period and rate of return, and you are going to bring both cost and benefits to the present value and compare and see whether it is beneficial to invest in this particular irrigation project or not. And we are going to compute the cost benefit ratio and also net present value. So these two indicators we are going to compute in irrigation economics as well as the drainage economics. So if the system is profitable at the required rate of return, that the decision is made to invest in the system. So this is a common sense. If you are getting the profits in the particular system, then definitely it's worth to invest in the particular project. So this is the overall project, but individually or seasonally, if you want to know or if you want to estimate the cost of production, so we need the crop water production functions with water and energy cost information enables to calculate optimum depth of water application. This is not only to estimate the the production cost, but also estimate economic I mean depth of water to be applied, so that the yield will be maximum, right, and the profit will be maximum. Okay. So and then the next is so the crop water production functions here. For example, the crop yield is a function of water applied during the cropping season. So here, for example, in the figure 1, if you see the applied depth of water, which is in and ET. So depth of water as well as ET on x axis, and then the cotton yield, that's called lint yield, that's in kg per hectare, and y axis. If you see the graphs, there are two graphs, one represents the ET and the other one is applied water. Okay. So here, so for a particular applied depth of water, right, so the ET results, ET based irrigation, that results the maximum lint yield compared to the water you applied, right, in the field. That means it has some losses. This is the total water or the gross water applied in the field. So that includes pre-irrigation, and then all other losses like runoff, depercolation, all other losses. Okay. So definitely, so this is one, and then the figure 2, you see this is the profit on y axis and depth of water applied on x axis. So if you see this, the crop price, so it contains two components. So this is the crop price and then water price, and when you subtract the water price from the crop price, and you get the profit. Okay, this is the profit graph, and if you clearly see at what depth, definitely the profit is maximum. So look at this, maybe at about 70. This point the profit is maximum. So that means the 70 centimeter of water needs to be applied to get the economic yield and also the maximum profit. Okay. And then, so the next is we're going to see the crop production functions here. Grims and Helzig 1990. So he gave a crop production function especially for the cotton. So here y a is the yield in actual yield in kg per hectare, is equal minus 395 plus 1067 into AWE. This is experimentally given water depth 0.5 54.15 into applied water. So, this is these relationships basically obtained from the experiments. So, AWE represents the applied water in experiments, field experiments. So, since irrigation often supplemented by precipitation, so sometimes you have to sometimes there are some precipitations during the irrigation, or if there is precipitation you do not give to irrigation. So, you need to add that the precipitation or effective precipitation in applied water. Okay. So, then the production function looks like this y a. So, this is the total water applied and then AWE. Okay. The above equation obtained of course the field experiments. So, and then the next is, so if the experimental irrigation efficiency is 90%, okay, so these production function what we have obtained is based on 90% irrigation efficiency. So, then the relationship between the gross depth of irrigation water applied and AWE. So, this is AWE, this is gross applied, gross depth of water applied, which is equal to a depth of water applied in field experiments divided by 100 minus 90 minus the irrigation system efficiency divided by 100, okay, or the experimental depth of water applied water is equal to gross depth of water minus gross depth of water into 0.9 minus n. So, n refers to this 90%. We assume that the experimentally determined AWE is related to 90% irrigation efficiency. Okay. So, n is the irrigation efficiency of field irrigation system, which is in fraction, and the other one is this. And pre-irrigation may be needed to germinate the crop. So, in not only the AWE, so you also have to apply the pre-irrigation that comes under grass. So, the most of this water is often wasted and leached or runoff. So, then the adjusted gross water depth applied to the field is equal to, so this we have already computed plus pre-irrigation. Okay. So, this is the gross water depth applied to the field for a particular crop, whereas AWE is the depth of water or actual depth of water applied to the crop during the experiments. Okay, so, then the cost here. So, irrigation cost here, water cost is normally calculated on volume basis, right, that is meter cube or acre foot and hectare centimeter. If the unit of applied water is centimeter, then the cost of water in dollar per hectare is equal to water cost is dollar per hectare, which is equal to this is the cost of water, right, in dollars into 100 into AWE, this is in centimeters. So, since we are looking for computing for 1 hectare, so the centimeter is being converted into meters, that is that is a meter by 100, and since it is 1 hectare, this is 10,000. Okay. So, then this gets 100. Okay. So, this 100 is from this. Okay. So, if only water cost is considered, then profit is calculated as, so generally profit is equal to, so production cost minus water cost, right. So, that is the profit. So, during the season, this is the product, once you get the yield and the resale value of the yield, or value of the yield minus the cost of water, that will give the profit, only if you are considering the water as the cost, and PR is the benefit or profit in dollar per hectare. So, the maximum profit can be found by setting the derivative. So, this we know because the graph which is going like AW and the profit. So, this goes in this. So, there is one place it is the maximum. So, that means dPr divided by dAW, which will be 0 at one point. So, that will be 0 and you get the AW, right. So, economic AW for which the profit will be maximum. Okay, here is example. Let us see, find the depth of water applied that results in maximum profit with drip irrigation system for the cotton CW crop water production function by Grimes and Elzig. So, that is already given in the previous slides. Assume that 7.5 centimeter precipitation infiltrates during the growing season. The cost of water is 0.0327 per meter cube dollars. The selling price of the cotton is $0.92 per kg. Assume that the pre-irrigation depth is 0 centimeter and AWE, which is equal to the experimentally determined AWE. The drip irrigation system efficiency is 90%. Okay, since it is 90% and AW definitely will be equal to AWE. Okay, so as per the formula is concerned. So, from Grimes and Elzig 1990. So, this is the previous equation minus 3954 plus AWU. This is PE, right, precipitation excessive or precipitation excess, and AWU. So, this is the kg per hectare. This is what production. Okay, this is the production, and now profit, which is equal to, so YA multiplied by 0.92, right. So, this will give the selling price, right, up to this, from here to here, the selling price of the crop, and then this is the water cost. So, water cost, this is the price of water into applied water. Okay. So, the maximum profit. So, with using this equation, so the profit function is being drawn, right, and from the graph, so the maximum profit you get at at about 79, for AW is 79, right, 79 centimeter, and you get the maximum. So, that will be equal to your $925 per hectare. Okay. So, this is $925 and you get this is 79 centimeter. Okay. So, using this graph you can estimate the maximum profit for which the available or applied water will be calculated. And then there is a second example. So, in this repeat the same example, that means you have 90 drip irrigation system, okay, and only but use the surface irrigation system here instead of drip irrigation system, change it to surface irrigation system and see how it is profitable with the 60 centimeter pre irrigation and 60% efficiency. So, there it is 90% efficiency. So, since it is 60% efficiency, so the field applied or experimentally applied water will be different from field applied water. So, here AWE, this is gross water, which is equal to AWE experimental divided by 100 minus 90 minus n by 100 plus 60. 60 is the pre irrigation, where here n for surface irrigation it is given 60%. Okay. So, then using the profit function, using the same profit function. So, this is for surface irrigation, this is for surface irrigation. So, for surface irrigation you are going to get the maximum, you are going to get the maximum profit at 623 here, and AWE here you get 74 centimeter. So, for 74 centimeter AWE you get $623 as a profit in case of surface irrigation. Okay. So, now depth of water applied AW gross depth of water applied in case of surface irrigation is equal to. So, this is applied water AWD AWE 74 plus 90 minus. So, same equation you can repeat it and then substitute the value 74 1 minus 0.3 because 90 minus 60 is 30, that is 0.3 plus 60, that is 166 centimeter. Okay. 166 centimeter you need to apply in case of surface irrigation. So, huge amount of water you need to apply. So, the annual benefit is decreased by approximately $300 per hectare. If you see, this is 623 and in case of drip irrigation it is 923 something like that. So, around you get $300 difference from the drip irrigation system, right, in case of example, the previous example. Okay. So, and not only that, if you see the gross water depth, so that is increased 166 centimeter compared to your I mean the previous example if you see. So, that will be around 74 centimeters something like that. Okay. So, this way you can analyze if you shifting to one irrigation to another irrigation whether it is profitable or not. Okay. And then environmental cost. So, previously we have only accounted for water cost. Now, for example, environmental cost also very important. Suppose in case of surface irrigation there is a lot of runoff and that carries lot of sediments from the field and definitely that pollutes the near water bodies. Okay. So, that involves the cost because you are dumping a non-point source of pollutants into the freshwater bodies. So, if you consider that definitely the profits will reduce. So, the erosion here, erosion from the sloping furrow irrigation system is used here example. Sediment kg per hectare is computed with this empirical equation, that is 10 power 3 4.6 to 10 power minus 3 into I power 3. So, where I is the seasonal gross depth of water applied by irrigation system in centimeter. Okay. So, this 7.84 into I square 0.77 I minus 9.44. Here is a graph, it is applied depth on x axis and then sediment on y axis. Okay. So, definitely, so increasing the water depth that yields more sediment and that runoff from the field to the nearest water bodies. So, the environmental cost NC suppose on per hectare basis is equal to, it is computed as dollar per hectare. So, dollar per kg, so this is the cost of sediment which is being added to the fresh water and kg per hectare is the yield of sediment from the particular watershed or the irrigation system. So, the profit here is, this is called, this is a production, this is the total income you get in the end of the season, then this is a water cost and this is the environmental cost. So, the crop income minus water cost minus environmental cost will be profit. Okay. So, then for example, including the environmental cost. So, here repeat example 59.2 where that is a surface irrigation system, remember, but include cost of erosion. The cost of erosion, land degradation and sediment removal from the river water is $0.2 per kg per hectare. So, because of I mean suppose the removal cost, the sediment removal cost is 0.2 from kg per hectare from the I mean water body where I mean the sediment from the nearby fields are being added to the system. So, the actual depth of applied water is used to calculate the amount of erosion. For example, the erosion depth AWE, which is experimentally determined applied water, which is 64 centimeter. So, that is I, this is a gross depth of water, AWE 1 minus 0.9 minus 0.6 plus 60. So, this is from surface irrigation system, the previous example. 64 by 1 minus 0.3 plus 6, this is 151 centimeter. Okay. So, this is the gross depth of water and sediment. So, with this gross depth of water, using this gross depth of water, estimating the sediment will be 429 kg per hectare using the empirical equation we defined before. Now, the environmental cost is 1 kg per hectare. For 1 kg per hectare you have $0.2 dollars. So, $0.2 for 1 kg per hectare into 429 is the kg per hectare is the sediment yield, and total cost of sediment is $80 $86 per hectare. So, using the above profit equation, the maximum profit 519 per hectare is found at AWE 64 centimeter with I equal to 151 centimeter. Okay. So, using the previous if you can subtract $86 from the previous thing, then you get 519, right, which is because that is around 630 minus 86 or 29, it seems 29 minus 86 you get 19. Okay. So, with this example shows that the optimal economic depth of irrigation is generally reduced when environmental cost of irrigation is considered. So, if you are considering the environmental cost, so the irrigation depth is going to reduce, okay, 151, and there it is 171, something like that, right. So, now whatever the production functions defined, this is experimented for a particular region. So, if you want to translate that to the different region, if someone wants to use the same production functions in another region, so FAO, that Food and Agriculture Organization has I am given a procedure or linearize the actual production function, so that anybody can use the production function. So, here for example, so the applied depth on x axis, lint yield on y axis. So, this is the actual curve, right, actual curve, and in order to linearize that, so this is the linear curve. Okay. So, how to translate this particular curve into linear curve? So, this is called linearization of this particular curve. So, it has a slope in the sense. So, this is x difference and y difference, and definitely delta y by delta AW will be the slope of this particular curve, I mean line. Okay. And knowing this point, right, knowing this point or at any of this point and knowing the slope, you can find out the line equation. So, let us see that. So, as I said, so this is finally you get the equation for linearized curve equation or equation of the line, which is equivalent to the curve. So, where y a is the actual yield, y m x is the maximum yield, and delta y delta a w is the differences in yields as well as water applied, and this is required, and this is experimentally determined a w and a w required. Okay. So, now we can also have the proof for this. So, like for example, slope here is delta y by delta a w, equation line passing through a w required. So, this is the a w required, and then y max. So, this is the y max, okay, this is the y max. So, knowing the slope and knowing the equation, so just substitute, this is the line equation, y minus y 1 minus m into x minus x 1, and then so if you can follow the procedure, like substitute the particular point in this is the slope and these two are the points, and then substitute it and then simplify it. So, here and finally, you get y equal to y max minus 1 minus percentage delta y by percentage delta AW into AW required minus AWE by AW required. Okay. So, you can go through the steps, this is easy steps, right. Now, example 4, to calculate the cotton yield, the required depth of applied water in the region is 100 centimeter and actual applied depth is 80 centimeter and the maximum yield is 1180 kg per hectare. So, this is the maximum yield, actual applied AWE 80 centimeter and in the region 100 centimeter, AWE 80 centimeter, maximum 1180, AW required 100 centimeter. So, from this graph, so this is already available graph from the experiment. So, use this graph. So, from the CPW this graph, what happened, so for 100% you get 1161 here, and then and for 40 you get 641, right, 641. So, substitute this, you get, this is the slope of this particular line. So, this, knowing this slope, so knowing this slope and knowing the other parameters. So, this is the slope is known and y max is known and all other parameters are known. Okay. So, now the actual yield will be 1000 kg per hectare. So, the term, this one is known as yield response factor, which is defined by FAO. So, if you bring that equation, rearrange the terms. So, that will be 1 minus y a by y max, k y into 1 minus AWE by AW required, and k y, this is yield response factor, which is equal to, this could be slope or 1 minus y I by y max by 1 minus AWE by AW required. So, so knowing the stresses, yield reduction due to different stresses, the combined yield can be estimated. This is the function of the stresses including salinity stress, water stress, nitrogen stress, pest stress and all other stresses. Okay. So, these are all in percentages. So, knowing the potential yield, right, knowing the potential yield E max, let us say E max multiplied by all, let us say yield reduction due to water stress, right. So, let us say water stress and yield reduction due to pests, right, and yield reduction due to nitrogen. So, all these things are in percentages and you get, this is the actual yield. So, let us see the example here for yield reduction. So, there is a 10% yield loss due to pests, 10% yield loss due to salinity, and the depth of applied water to the sugar beets is 90% of the required, and maximum sugar beet yield is 40 tons per hectare. What is the yield of sugar beets? So, here yield loss for pest and for due to salinity are given, and we have to find out yield loss due to water stress, and then plug it with maximum yield and you get the actual yield. So, use the above procedure, that is from the previous example. Find the percentage yield reduction due to water stress, that is y a 40, this is a y max, and 1 minus this is the slope of that particular curve 0.75, 100 minus 90. So, this is apply 90 percentage of that being sugar beet. Applied water to sugar beet is 90%. Okay. The depth of applied water to sugar beet is 90% of that required. Okay. So, that is 100 minus 90 by 100 and you get 37 tons per hectare, and percentage yield reduction due to water stress is 37 by 40, right. So, this much is actual yield divided by 37 by 40. So, that will be 93% and expected yield will be 40 into 0.93, 0.9 is due to the pest and 0.9 is due to the salinity. So, total you get 30 tons per hectare. So, the actual yield is 30 tons per hectare, not 40 tons per hectare, because. So, now next is the engineering economics. So, these whatever we have learned the previous slides, that is to estimate the economics or the profit for a particular season. Okay. So, knowing that, now you have to see whether investing such irrigation project is profitable or not. Okay. So, here the engineering economics analysis will definitely help to decide whether to invest or not. So, it combines the present, that is the capital investment, and future benefits, that is the crop yield and other benefits, and costs, water cost, crop yield, energy cost and labor, into one number, so that is cost benefit ratio. So, this is very important. As I in the beginning of the lecture I told, so there are two indicators, one is net present value and then cost benefit ratio. So, knowing the magnitude of these values, definitely will see whether investing in this particular particular project is beneficial or not. So, it shows whether conversion to pressurized system will ultimately result in greater profit or not. So, this is, and for example, conversion to pressurized system may result in lower water cost and greater yield, but higher energy cost or capital cost, because it has other components as well as a pump and all other components and that are really not requiring kind of surface irrigation system. Okay. So, this always trade off between the yield as well as the costs. Okay. So, it does this by converting all future costs and benefits to the present value based on the time value of the money. So, what it does, engineering economic. So, if you are putting some money in the particular project, so and the benefits you are expecting, for example, 10 years or 20 years time, right. So, if you are expecting $10,000 from the particular project, so it calculates, so the present value of the particular benefit and the cost, the present cost. So, then the compare present cost and benefits, and finally, it says whether investing in this particular project is worth or not. Okay. So, the required rate of return, this is the terminologies we use. So, the interest rate, so that a company expects to earn on investments. So, that is interest rate is the required rate of returns. In engineering economic analysis, if a proposed project returns a profit at the required rate of return, even if the profit is only $1, right, then the decision is made to invest the project. So, this is the thumb rule or common sense, that if you are getting profit of $1, definitely you go and invest in the project. The future value of money is calculated the following formula. This is F is equal to P plus P into 1 plus I power n, and n is the project life, and then P is the present value, and I is the interest rate, n is the number of years, and F is the future value. Okay. So, the same thing you can also get the for example, here if suppose $1 is placed into an account for 5 years at an interest rate of 6%, then the value of 5 years is, the future value will be $1.34. So, on the other hand, money that is received in 5 years is not worth as much as today and should be discounted. So, this is, I think, in the week number 11, in week number 11, lecture number 4, if you refer. So, we used discounting factor, right. So, that the same kind of concept will be using in irrigation also. So, the present value of money received in this future is, so this is the reverse. So, if you knowing the expectations in the future, you can also calculate what is the value in the present. So, for example, here in this example, the expected annual income from a project is $500 per year for 5 years, and the project requires $2,000 investment. Determine whether or not to invest in the project at two interest rates, one is 6% and 8% interest rates. Okay. So, here annual income is given. So, So, every year you are expecting $500 per year for 5 years, and the project requires $2,000 investment. So, investment is given. So, let us see, net present value at 6% interest rate will be, so f, this is the formula we will be using, and the for present value. So, P is equal to f by 1 plus I by n. So, this is what we expect in every year, that is 500, 1 plus 0.06 in first year. So, this is the value, and the same thing in second year, this is the value, third year this is the value, I mean in third year. So, all these things when you combine, so this will be the present value of the future value, okay, future price, present value of the future benefit you can say. So, the net present value will be present value of the 5 years expected income minus investment. So, this is this one minus income I mean investment is 2000, you get $106.1 if you I mean if you are going with 6% interest rate. So, similarly you can calculate for 8% interest rate. So, and since it is greater than 0, definitely you have to invest in the project. So, similarly you can estimate the present value of the worth of the benefits with at 8% interest rate. So, use the same formula, you get this is the present value of benefit at first year, present value of benefit of second year, present value of income in the third year. So, like that it goes. So, net present value is equal to present value of 5 years expected income minus investment. So, that will be negative. So, negative in the sense you do not invest at 8%. So, if you are investing at 6%, that is profitable, and do not invest at 8%. Okay. So, that is the meaning of this. And so, here it will give the typical annual maintenance cost percentage for irrigation system. So, this is the life of irrigation systems and annual maintenance cost. So, this will be useful while calculating the economics of irrigation system. And this is an example, determine the present value of the income from alfalfa 6 years from now at a required rate of interest of 7%. So, first assume no inflation, right, assume inflation cost of 5% per year and no inflation in the selling price of the alfalfa. The present value of alfalfa production is 631 per acre per year, operating expenses are 321 per acre per year. So, with this information, first if you consider the no inflation. So, inflation in this sense, so if you have a particular value of asset, right. So, that value will increase over the period of time. So, that is inflation. Now, present value of year 6 profit. So, that is 631 minus. So, this will be the 631 is a present value, right, and then this operating expenses. So, and so for that difference, if you can calculate what is the present value. So, that is $207 and cost inflated at rate of 5%. So, this is with no inflation, this is what present value, this is positive, and cost in the year 321, this is operating cost, because inflation is given on operating cost only 1 plus, and you get 430, and profit in the year 631 minus 430, you get 201 per acre. Okay. So, present value of here 6 profit with inflation. So, with inflation the present value. So, this is profit after 6 years and bring it to the present value. So, that is 134 per acre. Okay. So, with inflation you get 134, without inflation you get 207. Okay, cash flow diagram. So, this basically this will indicates. So, if you have invested in a particular project and expecting the benefit after 10 years, 20 years. So, you I mean you have to bring the benefits to the present value and the cost to the present value, and then compare, you get the cost benefit analysis or the net positive value, okay, net present value. So, all these with these three indicators in cash flow diagram will be judging whether investing in a particular project, drainage or irrigation project is beneficial or not with the particular interest and over the period of time. Okay. And this is about the irrigation economics. So, in this lecture basically we were looking into the project, I mean the economics of the whole irrigation project as well as the individual seasonal benefits. So, once knowing the seasonal benefits by knowing the production cost, water cost and then environmental cost, you will be estimating the profits of that particular year. So, then with that profits and then I mean if you have invested in that, you are expecting 10 years. So, every year you are expecting this much benefits, and using cash flow diagram or cash flow or discounting analysis or so all these economic indicators will be used to identify I mean to judge whether investing in this particular project is worth or not. Okay, thank you.